So now that we know that an electron has a spin and we need to include that idea into our wave functions, we can write any total wave function as a wave function for the space part and a wave function for the spin part. So that means that every wave function has a spatial part that depends on n, l, and m, and then it either has an alpha spin or an L and M beta spin, or some combination of alpha and beta. So if we think about our possible spin wave functions for two electrons, and remember that our electrons have to be indistinguishable, then we have the possibility of having electron 1 with spin up and electron 2 with spin up. We could have electron 1 with spin up and electron 2 with spin down, or we could have electron 1 with spin down and an electron 2 with spin up, or we could have both electrons being spin down. Now, if we operate the exchange operator on any one of these wave functions, so alpha 1, alpha 2, gives me alpha 2, alpha 1, which is exactly the same. So this has an eigenvalue of +1, so this is symmetric. I could do the same thing with both spins being spin down, so beta 1, beta 2, operate the exchange operator, gives me beta 2, beta 1, that's exactly the same. So that's a +1 eigenvalue, and that is also symmetric. But as we have these written, they are not eigenfunctions of the exchange operator. And so we have to write them in terms of linear combinations. So for these two spin functions, we're going to write alpha 1 beta 2 plus alpha 2 beta 1, or alpha 1 beta 2 minus alpha 2 beta 1. And these will be eigenfunctions of the exchange operator, just like we saw with the spatial wave functions. And this one is going to have an eigenvalue of +1, so it is symmetric. And you can convince yourself that this one has an eigenvalue of -1, and so it's anti-symmetric. And so for two electrons, we have 4 possibilities for the spin wave functions. 3 are symmetric, and 1 is anti-symmetric. So let's think of our 2 electron space wave function where we had 1 electron in 1s and 1 electron in the 2s orbital. And we said that we had to write these as linear combinations in order to make them eigenfunctions of the exchange operator. And so we had one linear combination where we added the 2 possibilities of how the electrons were placed in those orbitals. And we had one that was the subtraction of those 2 possibilities. And this wave function was symmetric because its eigenvalue is +1. And this linear combination where we've subtracted is anti-symmetric because its eigenvalue will be -1. So we're going to call this psi s for symmetric and this psi a for anti-symmetric. So those are our spatial wave functions. Our full wave function is the space wave function times the spin wave function. So notice that if I take a space wave function that's symmetric, it has an eigenvalue of +1, and I combine it with a spin wave function that is also symmetric, so alpha 1, alpha 2, for instance, is symmetric and has an eigenvalue of +1, that with exchange, I will still get an eigenvalue of +1 because +1 times +1 is +1. And so symmetric times symmetric gives me a symmetric wave function. However, if I take a symmetric times an anti-symmetric, that's like taking +1 times -1, and I get minus, and so that gives me an anti-symmetric overall wave function. And if I take anti-symmetric times anti-symmetric, then that's like taking a -1 times a -1, which gives me again a +1, and so that gives me a symmetric wave function. So if I want a total wave function that's anti-symmetric, then if my spin part is symmetric, my spatial part has to be anti-symmetric. And if my spatial part is symmetric, my spin part has to be anti-symmetric. And it turns out that when we have electrons or any particle with a half integer value of spin, so any particle with a spin quantum number that is half integer is called a fermion, and they have to be described by anti-symmetric wave functions. And so our electrons must have anti-symmetric wave functions, and so our only possibility is to combine a symmetric with an anti-symmetric. So a symmetric space with an anti-symmetric spin, or a symmetric spin with an anti-symmetric space. So let's see how this plays out if we have a ground state helium atom. So helium in its ground state has a spatial wave function that is 1s squared. In other words, the first electron is in 1s and the second electron is in 1s. And this spatial wave function is symmetric with respect to exchange. So since our spatial wave function is symmetric, that forces the spin wave function to be anti-symmetric. And so we have to write our full wave function in terms of this symmetric spatial wave function times the anti-symmetric spin wave function. And so the anti-symmetric spin wave function, the only choice we have is alpha 1, beta 2, first electron spin up, second electron spin down, minus second electron spin up, first electron spin down. That's the only possibility for an anti-symmetric spin wave function, and we have to have anti-symmetric with symmetric space in order for our whole wave function to be anti-symmetric. So this means that if my two electrons are in the same orbital, that will lead to a symmetric space wave function. So if my two electrons are in the same orbital, my spins must be different. When electron 1 has a spin up, electron 2 has to have spin down. And when electron 1 has spin down, electron 2 has to have spin up. And so we state this as the Pauli exclusion principle, because this works for more than one electron, or more than two electrons, that if electrons are in the same spatial orbital, their spins must be different. So if we define a set of quantum numbers, n, l, m sub l, and m sub s, for each electron, then every electron must have a unique set of quantum numbers. So in other words, if n, l, and m sub l are the same, they're in the same orbital, then m sub s has to be different. If m sub s is the same, then something about the spatial orbital has to be different in order to make sure that we have an anti-symmetric space and a symmetric spin, or a symmetric space, everything the same, and an anti-symmetric spin, different spins.